Okay, then we learn about scale factor and Minkowski space. Scale factor. Okay, very good. Anything else? You can speak also. FRW metric. Okay. Scale factor and early universe. Priyanka, you can send direct message. Everyone. Yeah. So FRW metric and cosmology is the study of the universe and evolution, birth. Anything else? Anything else you remember? We talked about what are the different epochs. Can you tell? We talked about different crucial point of the universe. Okay, first is also we talked about singularity. You remember? What is the singularity? When is the singularity? At what point? Can you speak or write down? Yeah. Yes, Gauri Shankar, you can speak.
T is equal to 0 when
T equals to 0. We don't know what is happening at T equals to 0, but we know that A equals to 0. Yes?
Yes, yeah.
A equals to 0 is going to be singular because the space-time breaks down. Same with happens in the black hole center. Okay. Anything else? What are the important epoch from starting after A equals to 0? Then what are the few milestone of the universe? Can you write it down? We discussed. Even if you don't understand it, we know that what happened one by one. We discussed few things. Did you do the homework? That at what scale factor we did? So first is the Higgs. Okay, Higgs got mass. That is called the God particle getting mass before, because in the beginning everything was massless. Jahan is saying nucleosynthesis. Very nice. What is the time scale of nucleosynthesis? Anybody remember? 3 seconds. Very nice. A equals to 10 to the power minus 6 actually is much. No. Time equals to 10 to the power minus 6 is not nucleosynthesis. That is QCD work. Making in the nucleosynthesis means basically in cosmology, you are right, Avinash, but generally in cosmology, nucleosynthesis means formation of hydrogen and helium. Okay, so that happens at 3 seconds. What else? After that, so first 3 second particles got mass, then we got nucleosynthesis, 3 second helium, hydrogen, but was helium and hydrogen was fully like an atom or something else? It was, we discussed, no? It was ionized, very nice, plasma. Why? Because the photon temperature was much higher. And then universe cools down like a thermodynamics gas. And as it cools down, when it comes below 13.6 electron volt, that is the energy of the first orbit. You remember in your class 12 physics that 13.6 electron volt is the energy of the ionizing energy of the first orbit. Yes. So when universe temperature drops below 13.6 electron volt, then the photon cannot ionize. Then the first atom, hydrogen atom forms. Okay. And the photon which was released, because now photon does not scatter with electron. And if it does not scatter, it will not do a random walk in the plasma because it becomes free from the plasma because it cannot give energy to the, because energy is lower than the atoms, ionizing atoms. So if it cannot interact in quantum mechanics or quantum field theory, it is said that if you don't interact, you will move freely. So what happens today, this is Earth, okay, Earth, and okay, let me draw with it. So this is Earth, I am drawing it. And we are seeing that photon which was released when universe temperature was 13.6 electron volt. It happens. What is the time scale? You remember? I told you how old was universe that time. Any idea? Let me see whether you remember or not. How old was universe? 0.3 million year. Very nice, Jahan. So it seems like Jahan has done the study. So I'll tell you the book of cosmology. It's called Kolb and Turner, and sorry, not Kola, Kolb and Turner, and there is another book by Scott Dodelson. Both are available in Flipkart. So what is the name of the book, Ravi? Scott Dodelson? Physical cosmology or modern cosmology? I always forget.
Modern cosmology.
Modern cosmology. It is available in Flipkart. It's a nice book. You can study. Yes. But I'll also give you the notes. That notes are not from that book, but it is good to have a book, okay, so that you can study. Okay, so 0.3 million year after the Big Bang, photons were released. So from that time till now, these photons are traveling. Yes or no? Yes or no? Yes, because it has become free. It is traveling. Agreed? Because it is not interacting with it. So if you see that photons is traveling, if you see in the sky, and that was the Nobel Prize, that there was two engineers. They are the electrical engineers. They work with antenna, TV antenna and all this thing. And they were looking at some signal, and they saw that they are getting a very low temperature photon, because this photon is traveling from Big Bang. They didn't know that time. They got some low temperature, like microwave range wavelength noise coming into their antenna. And they thought initially that it is coming from some stars. But then they changed the direction, they again saw that. Then they rotated every direction, the antenna, they saw that it is coming from every direction. So then, to make it confirm, they changed their land, means they went to another continent. From US to Europe, they saw that they are getting it there also. So if it is coming from every point and everywhere, that means it is not coming from a stars or galaxy or anything. Is it clear? Because if it comes from star or galaxy, it will be coming from one direction or 2-3 direction. But if it is coming from every point, then only one option is there. What is that? Who can write? It has to do from the early universe. Because early universe, the photon was filled everywhere. You know, it's not that one point photon was. There's this decoupling of photon from the atom. Ionization was happening everywhere. Yes, because everywhere the temperature was going down as the universe expands, like the balloon expands. Is it true? Yes. Yes. So that's why if you see the sky, you will see that temperature is, that photon is coming from all direction, but you will see it like a I am drawing it. Like a 3D Max movie screen. You are here with equal distance in every direction. You see that photon are coming. So why you are seeing a specific surface? Can anybody tell? Why we don't see that photon coming from here? Who can tell? If you want to catch that microwave photon coming from that 13.6 or below, when the hydrogen atom was first formed from ionized plasma, because there was not enough energy to ionize, why it is coming from a disk? Why it is not? Why you cannot see it from here? Can anybody speak? This you don't need to write it down. Any guess? Now it is your time to guess. If you don't be shy, any idea? Or no idea? At least say something. No idea, or some idea. Okay. Who has any idea? Why you will see it like forget about this, you will see it like at one radius. Why it has to do that radius?
The light was from 13.8 billion years
Very
ago.
nice, very nice, Jahan. So see, what is the age of the universe now?
Almost 14 billion years, 13.8.
13.7 billion years that we talked yesterday. Yeah,
Yeah.
last class.
Yes,
And
yes.
it was released like 0.3 million years old. So 13.7 billion minus 0.3 million is almost like 13.7 billion. Yes?
Yes.
So that photon, you cannot make it stop. You know that photon cannot be stopped. It has to move in the speed of light. How many? Everybody with me? Yes? Yes? Give me a thumbs up. Yes. So if it has to travel, that means you have to go back in every direction, and 13.7 billion minus 0.3 million years back when this thing was released, you will find a distance. So this is the fact that it comes from every direction, and because if there is a photon which is coming from inside, say it is coming and reaching you, there was also photon that time, because in this space also there was a hydrogen atom was released, because this ionization to formation of neutral hydrogen happens in every point, but the photon which was here, it has already crossed and traveled somewhere else, because this distance is half of the space. Is it clear? So to see today, you have to see a surface, and that surface is called surface of last scattering, LSSS. Surface of last scattering means that is the last time hydrogen के साथ the photon scattered, and after that it never scattered. So that is called surface of last scattering, and which has been observed by WMAP satellite. After the discovery of this antenna people, they got Nobel Prize. They are called Wilkinson microwave, and their name is Wilkinson. And then WMAP and now Planck.
Sir,
Yes.
is there a chance that these photons will somehow vanish or attenuate or something?
Actually, this does not. It could have, but this photon does not it is not a localized photon of any other particle. Some of them might get interacting with some particle, but its energy is so low that it is on microwave. You cannot interact with electron or other particles of the universe. So basically, it is shown that you see most of the space is empty space. You know that, though it feels like universe is filled with stars and gas, so most of the time they will come, once in a while they will hit, but as a whole you get majority fraction of the photon coming, it will not get obstructed. So that's why we see them today in everywhere.
Okay, so with time will the energy again decrease?
Yes. So that's today the wavelength is, anybody knows what is the wavelength of cosmic microwave background today? Anybody have? Or the temperature, who knows?
Temperature is about
Temperature is around 2 Kelvin.
2 point something, how much?
2.7, I guess.
2.7 Kelvin, very nice. 2.73 Kelvin. So it's a pretty low temperature. Zero temperature is Kelvin, zero is zero. So it's almost close to zero temperature. But, and if you find out its corresponding wavelength, it will be in the microwave. You know that. If you know the temperature of photon, you can find out its wavelength. Yes or no? Yes? That is your homework. That relation between temperature of a thermal photon, black body photon, it is like a black body reaction, black body radiation, and it's coming 2.7. But when it was released, it was not 2.7 Kelvin. Okay? It was much hotter. But as the photon travel, as I told you last time, that everything in the universe gets stretched as the universe is expanding. So its wavelengths also get stretched, yes or no? So its wavelength become red shifted or blue shifted? Can you write it down? Red shifted or blue shifted? Red shifted. That means lambda becomes higher, so that means energy becomes lower. E equals to hc by lambda. So red shifted. So that's why later in the class I'll tell you that the scale factor, maybe today only you'll get to know, scale factor when this photon was released is a equals to around 10 to the power minus 3. Okay.
Excuse me, sir.
Yes.
So, when photons get redshifted, that means their energy is decreasing, right? So,
yes.
Then where is this energy exactly going? Because the total energy is conserved.
It's a very nice question. I will come to that. Basically, to give you the answer, photon has a pressure, and universe volume is expanding. So when you have a gas box where you have a pressure, then you have a work done, P times dV. You know that. Yes. Yeah. So here in universe, as universe is expanding, there is a work done with pressure. The photon is not pressureless. That we'll do later. So very nice question. That PdV part sucks that energy. Okay. Good.
Okay.
So that we'll do it later. Exactly. Any more question? So the scale factor was 10 to the power minus 3. Okay. That means the scale factor started with very low, 10 to the power minus 40 or minus 50. We can go up to till that much because we cannot go to A equals to 0 at the Big Bang because it is a singularity. But 10 to the power minus 40 to 10 to the power minus 3 means universe has become pretty big. It's almost 10 to the power 35 or 37 times in every direction. Scale factor stretches every direction. Is it true? You remember the coordinate gets stretched? And today, the normalization is today the scale factor is A equals to, it's a definition 1. Okay. So how we make it 1? See, we only know the ratio of how scales changes. We don't know the absolute value. So there are two ways to normalize it in physics, any system. Either you normalize it at the beginning of Big Bang and then you say like, okay, it has become 2 times bigger, it has become 10 times bigger, it has become 10 to the power 5 times bigger. But then we'll end up with a very large number today because every time we'll write an equation, we have to use a factor 10 to the power 40 because scale factor has become almost 10 to the power 40, 50 times than the Big Bang. Rather, what we do, we say that today it is 1 and we make it smaller in the past. It's the same way because the ratio remains fixed. Is it clear? Yes, that is called a normalization. Is it clear? Either you can fix it in the beginning and increase it, or you can fix it now and decrease it because we only know the ratio. So today A equals to 1. CMB happens at 10 to the power minus 3. Nucleosynthesis happens as 10 to the power minus 11 or 12, the hydrogen atom form, and QCD happens at 10 to the power minus 17 or 18. That you need to see. It is in any Google search you do, scale factor versus different epoch of universe. That was your homework. Okay? If you have not done it, please do it and make a note and send it to me. Even if you copy it from somewhere, it's okay. Scale factor and time. Either you can use time or you can use scale factor. Both are given in the Google search or in many books. Is it clear? So Higgs phase transition, mass, QCD phase transition, Big Bang nucleosynthesis, then CMB, that 4 things you need to tell me. Okay? And maybe formation of first star. I told you last time, 4 or 5 billion years back. That time, what was the value of A, scale factor? Clear? This is your homework. You have to do it and send it to me. Okay, very nice.
Sir?
Yeah.
If the energy of the CMB radiation is decreasing subsequently,
yes.
Is there a chance that we lost some radiation before?
We
lost some radiation, like.
No, we lost. No, its energy is decreasing because it's getting work. It is doing an work done. We'll do it later. So it is conserved, but it is going in the form of work done in expanding the space because there is a pressure of photon. Okay? You remember, no, in your thermodynamics class of BSc, that any kinetic energy gas has a pressure P equals to 1/3 rho c square. You remember this 1/3 factor? Or if you have done statistical mechanics, for gas, quantum gas in BSc, Bose-Einstein formula. Then you will also get a formula P equals to 1/3 rho. Anybody remember? Anybody? Yes? You have done or no? BSc physics, anybody done? The pressure derivation, yes or no? MSc we had. Okay, very nice. Last sem. Yes, Avinash. Okay, other people? Shruti, Arpita, Gauri, Priya, Avinash? Yes, so you have to answer. Okay. Okay. So now this is the completion of introduction of basic events, so that you have now basic idea. Now we'll get into the mathematics. Okay. Now onwards, I'll keep sharing one note. I'll scroll down. Okay. Now you are only seeing my video. So as I say, time to time, we'll come and turn on our video, so to give a presence that we are all here. Okay. So please turn on the video and say hi. In COVID time, you are all in the home. Okay. It's better to take a break and say hi. And if you have any questions, you are enjoying, turn on the video. As I say, time to time, we'll do that. Okay. So Jahang, you are enjoying? Yes? Yes.
Yes.
Very nice. Shruti, you are joining from where? Gujarat? Chennai. Okay. And Gauri, you are, I forgot. Where are you joining from?
Kerala, sir.
So you are all enjoying? Yes. Now we will go into the scrolling down of the notes. I'll send you the notes. Anytime you have some question, you can unmute and ask the notes. Okay. Now the basic part is done, the idea. Now we'll get into the mathematics. Okay. Yes.
Yes.
Okay, very nice. Okay. So you can now switch up the. I'll be sharing the notes. You can see it. Give me a thumbs up. Yes, good. So see, last time we did this metric, dA square is equal to C dt square. They are using this convention, plus for light, minus for the space. You can do it other way around. So then your C square dt square, this is the length scale. And we know that Minkowski metric is eta mu nu dx nu, where mu runs for 1 to 4 or 0, 0, 1, 2, 3. 0 is for time, 1, 2, 3 is for, you know that, no? This convention of summation, how many of you know? Yes. Anybody don't know? Please write it down. It's okay. Otherwise, you just look into any book. It means mu you have to run and nu you have to run all from 0 to 1. But as the metric is diagonal, eta mu nu, only the 1, 1, 0, 0, 2, 2, 3, 3 component will survive. All cross component, eta 0, 1, eta 1, 2, eta 3, 1, all will be 0 because it's a diagonal metric, Minkowski metric. So I have written the Minkowski metric in the right side. And this is a shortcut way, eta mu nu dx nu to tell you what is the distance in the space, and eta mu nu is the metric. Is it clear? So now, if somebody gives you the metric of the space-time, you basically know the geometry. Yes, clear? Thumbs up. As I talked about the distance, because as I say, that distance tells you the geometry. We show that example of in the curvature of space. Okay. Now, let us go into the spherical polar coordinate, and you can write down in your notebook that, let us all write down once the metric. Okay, you all have notebook with you?
Yes, sir.
Yeah. Okay. Please write down the metric once. So that you know. So dr square is it clear, the metric? Now there is one extra term has entered in the metric. Who can say? Which we did not discuss.
K.
K. Very nice. K is a number. K is called spatial curvature. So see, till now we have taken the expansion of the universe and the Minkowski matrix, we multiplied it with the AT term. But now, who knows that universe itself, the 3 space, that means r, theta, phi, can itself be a curved space-time in a higher dimension. So that K is called, if you go into the mathematics, we'll not go into the detail, forget about time as a dimension, you can just even go into 3 dimension and you can make different geometrical surfaces. Possible? Yes? Yes? Like this. It is a 2 dimension. I can make it twist like this. Then it will be a curved surface like that. Or a cylinder, it is a curved surface. It is a different, it is a 2D curved surface. Yes? Agreed? So like that, 2D you can imagine that it's a curved surface, but 3D you cannot because we are in 3D. So if it is a 4 dimension, then you can see that we imagine. Is it clear? So that curvature K is the curvature of space itself. Okay? This K turns out to be 0 by observation. So that's why we live in a flat space universe. But it could be that our universe's 3 dimension could be curved in a higher dimension, but we have not seen that. But this K term is not 0 as a whole it is 0, but is it 0 everywhere in the universe? Is the universe curvature 0 everywhere? Who can give me the answer? You know that. You have
No,
seen.
sir.
Huh?
No, sir.
No. So where it is non-zero?
Where there is mass.
Where there is heavy mass. So near black hole it is non-zero. Is it clear for everybody? Yes? So you have a spatial curvature at different points. Even if you go near sun, you know that the light ray bends. During the solar eclipse, we have seen that. That's why the Einstein's theory got proved. Light ray bent not because of refraction, just because the space itself is curved. Do you know that? Yes? How many of you know that? Otherwise, okay? Yes. As we told, that if you put a heavy mass, we'll take a class on GR on with you. One session we'll take towards the middle. Then, if you suppose you put sun, so this is flat. You put sun, it will become curved. So now light ray also has to travel through the curved path. So it will bend by some degree. By sun, it is very low curvature because the mass is not enough. But black hole side, the curvature is pretty huge. Clear? So our universe is flat. It's a global definition, not local. So that's where the cosmology, I am coming there, has these 2 assumptions. Cosmology is called homogeneous, act 1, and number 2, it is isotropic. Homogeneous and isotropic universe for cosmology. So what does it mean, cosmology? Cosmology means you treat the whole cosmos as one object. So in cosmology, it is an example. Suppose you have a water jar. If you go and take a microscope, what you will see? It has molecules. It has interspace distance between molecules, water molecules. There is empty space. But if you come in a longer distance from the above, you will see water as a homogeneous liquid. Yes? Yes? Agreed? But if you go microscopic distance, you don't see it is a homogeneous liquid. You see the different over density, under density. Agreed with me? Is this clear? In the same way, if you look from Earth, this is a local universe. You see here, star, empty space between moon and sun. I mean, empty space between Andromeda galaxy and Milky Way galaxy, empty space between North Pole star and other stars or constellation. But if you go to a very large distance, what is that distance? Around megaparsec. Why megaparsec? Because see, the galaxy distance is kiloparsec. You know what is parsec, no? How many of you know what is parsec? What is parsec? Can you write it down? What is parsec? In parsec in light year, who can tell me? 1 parsec is how much light year? Okay, 3.26 light year. Very nice. What is the diameter of our galaxy? Anybody can tell? A Milky Way galaxy. You have done a lot of astrophysics study. 10 kiloparsec. So 10 kiloparsec means 10,000 parsec. So in light year, how much it is coming? Can anybody, not Ravi, somebody else can calculate it in light year? All of you should do. How much light year is the diameter of our Milky Way galaxy? Let's get an estimate. Once done, you type it down. Okay. 3.26, yeah, 10 kiloparsec. Okay. Okay. So 0.3 into 10 to the power 5. Yeah. So light will take so many years, 32,600 years to cross, almost like close to 0.1 million light year. So you can see that how big is our galaxy. Light takes only 8 minutes from sun to here. It's a huge distance. Here light takes 32,000 years. But that distance is also very small distance compared to cosmology. There are millions of such galaxy, billions of such galaxy in a galaxy cluster. That size is megaparsec. Okay? So kiloparsec is size radius of the galaxy or diameter, and intergalactic space is around 100 kiloparsec. That means if you go for another 100 kiloparsec, you will find another galaxy on an average. Of course, there is fluctuation. Or like 50 kiloparsec or 100 kiloparsec. Okay? And then many such galaxies get clumped into, billions of such galaxies clump into a cluster called galaxy cluster. There are many such clusters has been observed by Hubble Space Telescope. Each cluster has billions of galaxies. Their size is 100 to 200 megaparsec. Mega means million parsec. Clear? Clear? And the Hubble horizon, as you are discussing, that universe is infinite, but you can see only finite. That starting from 14 billion years back, light has traveled. That distance is around 3000 megaparsec. So let us write 3000 MPC is the more or less the observable universe today. Then 100 MPC is cluster, where within the cluster of galaxy. Then if you come to smaller, then 10 kpc is size of the galaxy. Clear? This one? So cosmology is a study, you have to go in the cluster at least length scale. So if you go in 100 megaparsec distance, and from there, like when you come out of the water jar, if you come out of that large distance, no, compared to the intermolecular distance, if you go to a bigger distance, so our distance is like 100 megaparsec or beyond, then every galaxy, everything will look like a homogeneous liquid for the universe. You cannot distinguish between galaxy, intergalactic space. It is exactly like a water jar. And that's why cosmology assumption is it's a homogeneous and isotropic universe. Means it's similar in every direction, and similar in every point. The laws of nature is similar in any point and similar in any direction. Is it clear? Clear? But if you come to solar system and find the density, it will be 10 to the power 33 times higher than the cosmological density, because you have come to a very local heavy zone. So to find the cosmological density, you have to average over a much bigger volume. Is it clear? Yes? Yes? So that's the way of, so that's why on a large scale, cosmology universe is spatially flat. But if you come to black hole, of course there is curvature. If you come near sun, also tiny curvature. But if you go to a large scale, you see then every masses effect gets nullified because it's a homogeneous cosmology. But still there, we could have that the space is twisted because we know there is higher dimension, but it is not. Means higher dimension may be there, but we know that our space is not curved. And that's why k equals to 0. Is it clear till now? Any question? We are speaking, but these are very important concepts of cosmology. Now, I have explained you that astrophysics is different than cosmology. Is it clear? Yes? So you go to a cosmology now is a study of universe at a much larger length scale than the things we do in the solar system or our galaxy scale. Okay? And you can treat whole cosmology as a homogeneous gas or liquid. And that's why laws of thermodynamics applies there. Because you cannot do a laws of thermodynamics with an inhomogeneous system. Yes? You cannot apply laws of thermodynamics in solar system. Okay? Where is the pressure? Where is gas? Because the maximum space is empty. Okay? Good. So now, as we have known that k equals to 0, let's move down then. So now, as I have said, AT, I have told you yesterday, last class, that we did not take scale factor only depending on time, not on space, because of the isotropic universe. Okay? Scale factor overall time dependence due to the expansion of the universe, AT is solution, and AT is isotropic. That's why no space enters. And k will keep this term now 0, 1, and -1. Please go and read to Dodelson book or Colvin Turner. Dodelson book is also available online. I think some PDF copy. If universe is 0, it is called flat. Universe is +1, it is called closed universe spatially, and a -1 is open universe. This is your homework to study. Okay? So now, let us go here. I told you in last class that if you know the metric, you can do quite a few things. You remember? You remember? Yes? Now we are going into the mathematics with FRW. So here it is. So the metric is this. Now, who can tell me with unmuting the mic, because I am sharing the screen, I don't see you that much, that for light ray, what is ds? So what is the space-time interval ds for a light ray? Who can tell? Have you read it in special relativity?
Is it 0?
What is it? Huh?
Is it 0?
Yes, it's 0. ds square is equal to 0 because c dt is equal to dx. Because c dt is the time traveled by the light, is the distance dx, isn't it? Yes? So c square dt square is equal to dx square. So for light ray, it is a well-known fact that ds is equal to 0. Is it clear for everybody? This is very important. How many of you did not know that ds equals to 0 for photon? This is special relativity. Okay? Why? Because c dt metric is what? C square dt square minus dx I square plus ds y square plus dz. And dxi dy j dz square is the distance. and c dt is the same distance light travel. If the velocity is less than c, then you will get light-like curve or space-like curve depending on that. Okay? So time-like curve or space-like curve. But light-like curve means ds is equal to 0. This you should know from special relativity. So now, let us take k equals to 0 now for flat universe. Now, if you also take a situation where you only take a radial light wave. Okay. So now we are going to do like this. Suppose you are here, this is your coordinate system, and you are only taking a radial light wave. This is the distance dr. Only the light is traveling radially. You are not taking a light which is bending. You are taking a light which is directly coming from a star. So if you use it in the metric, what you will get? Can you write it down in your notebook? So ds square equal to 0 for this light. So you will get a relation between c square dt square and at square with dr. Please write it down. It's easy. K equals to 0. Actually, you can keep the k also. Just it doesn't matter. K equals to 1 or 0. Doesn't matter. You can keep. So you get this equation. Can you say in loudly? You got it? Is it clear? Yes?
Yes.
Give me a thumbs up or something, because I am not able to find out whether you are responding or not. Yes? Is it clear, or if you have any questions? Many of you are not asking me any questions. If you don't ask any questions, whether it is stupid or a real question, doesn't matter. If you don't ask questions, you will not learn that much. Okay? So better to ask questions. So any question till now? Or is it clear totally? Clear? Okay. So now, here we have used d theta equals to d phi equals to 0 because we are only looking into the radial movement. So a star at a distance r or r1, radiating light, it is coming to us radially. Assume it is not curving. Then dt square is equal to this, at square, dr square. So dr square is the distance, radial distance, k is the curvature of space. In between, maybe there is a black hole, some curvature is there, who knows. And at square is the scale factor of the universe. This is what you get. Now we have to integrate this. So now I want everybody to look into, I'll stop this one so that you know it. So say that there is a source Rs. Rs is the source, star. And it emits one photon light at a time t emission, Te. And we get the light at r equals to 0, but at the time t naught, t observed. This is the notation. So when it is emitted, Te, and it is observed at t naught, 2 different times. Okay, there will be some gap. And what distance it was emitted? This Rs. And this is 0. Now Rs is that coordinate distance, which does not change because of the expansion of the universe. You remember? I saw that x1, y1, z1, it does not change. How many of you remember? Yes. This coordinate sometimes is called co-moving coordinate. Co-moving coordinate means it is moving with the expansion, so it does not change. Co-moving coordinate. So in x1, y1, z1 in Cartesian, but here it is r in spherical polar coordinate. Theta and phi, we are not so much interested now. So can you write it down now? That, okay, you don't need to write it down. I'll say, I'll integrate this. So now see, left hand side. Te, I'm integrating it, emission time to the observed time, T naught. I have brought down AT in the time side because I have to integrate all the time derivative. Then what is remaining in the right side? See, TE and T naught is sorry, in the right side, you have, okay, TE to T naught. Origin is R equals to 0. Okay. So I think there might be a minus sign here because it should be RS to 0. Because TE is at the RS and 0 is it true? Because T naught is when we are receiving at R equals to 0. Okay. But anyway, even if there is a minus sign, let it be. You can write down the minus sign. So is it true? Is it clear for everybody now? I want to integrate now this thing. Just using the formula for light ray with using the metric, because ds equal to 0. Anybody has any question? Now we are getting into little bit derivation of something very important. Is it clear, or you have any question? Either if it's clear, you give a thumbs up. If you have any question, you ask me to say it again. Avinash said clear, Gauri said clear, Jahan clear, Shruti clear, Priyanka clear, Arpita clear. Okay. Ravi, it is clear? Yes. So now, light ray is emitted from there as a pulse. You know, light ray comes like this. Say like a pulsar is coming like this, pulses. One light, another pulses. So the first one is emitted at TE and received at T naught. The second one is emitted at a time TE plus delta TE, little bit difference. So second one is emitted at, I'll come in the node, it is there, and it is received at T naught plus delta T naught. Because the interval will not be same, because you'll come to know. That's because the space is expanding. Okay? So now let us go there. This is a very important derivation. So now say there is a second pulse gets emitted, which is at a time T naught plus delta T, second pulse of light, like this. The peaks are called pulse, peaks, okay? You can see my video. Peaks are called pulse. First pulse, second pulse, like in electronics course you do, okay? So now you tell me the second pulse is reaching us at T naught plus delta T naught. But does the right hand side change? Yes or no? For the second pulse, you have to unmute and tell yes or no. For the second pulse also we get a equation, no, like this. T plus delta T plus T naught plus delta T naught. This, the right hand side will change or not?
No, sir.
Anybody else?
Sir, only coordinates are fixed, right? But the distance between them is...
But here we are only using the RS, the co-moving coordinate. No distance part, we are not talking. Who tells that the right side is the distance? Not yet. The total distance is actually 80 times that thing. Okay?
Yes, sir. Okay. Yeah.
Got the point? So it is just a mathematics now. Just look at the mathematics. Right side, it does not depend. As long as the coordinate of the star is fixed, the star does not move with peculiar velocity or something else. As long as it is only moving due to the expansion of the space, RS is fixed, as we discussed last class. Yes? Yes?
Yes, sir. Yes, sir.
So right hand side is same for the second pulse, and that gives you, you see, this equals to same as the right hand side. So then you get this equality. TE to T naught is dt by AT equals to T plus delta T integral T naught plus delta T dt by AT. Just equating these two for first peak of the light and the second peak of the light, as the middle part dr by 1 is the same for both cases, so they has to be same. Is it clear? Yes?
Yes, sir.
Yes, very nice. Now this is your homework. From here, this simple equation, you have to show dte by at. Delta t is basically the time difference between two pulses at the point of emission. Means say pulses are coming from a nearby galaxy. The two pulses has a time difference delta t divided by ate. Ate means the scale factor universe at the time of emission equals to delta t naught, the interval we see between two receiving pulses, by at naught. This is your homework. For that, it is not so easy, but hopefully you will be able to do that. You have to expand this definite integral. You remember class 12. You will see some term will get cancelled, and you have to expand in Taylor expansion little bit, because you have to use the fact that delta t is much less than t, and delta t naught is much less than t naught. So there will be an expansion. You can do that, and this is your homework. You have to spend some time to get it. Is it clear? Is the homework clear? That right hand side equation, delta te by at is equal to delta t naught by at naught. This you should be able to do that. So now look at the next equation here. Now if we think that these pulses as the peaks of a wave trains, we know that the light wavelength at emission is lambda e is proportional to delta t, because that's the difference between two wave peak. So the wavelength comes like a train, no, in electronics. So it is here also, in light also. So lambda e emission is proportional to delta te, the interval between two pulses peak. This is clear from here. Is proportional to lambda emission. And receiving, maybe the interval between two things will be lambda observed. So now, this is very interesting. Delta TE by delta TE, we have, forget about lambda observed and lambda emitted. Just look at this equation. Delta TE by delta by ATE, which you just derived, you have to derive at homework. So bring the delta T naught by delta T one side and AT naught by AT in one side. Okay. So now I will do it here, otherwise you will get confused. So what we have found, can you tell me? Delta TE by APE means the difference equals to delta T naught by AT naught. These are the scale factor at the emission, scale factor at the receiving. Now if I multiply both sides by c, velocity of light, what will be the c times delta T? I just said it is like lambda emission divided by ATE equals to lambda observed by AT naught. Is it clear? I just multiplied both sides by c. C dt is lambda e, c dt naught is lambda naught. So now lambda observed by lambda emission, I am just taking the side change. Lambda observed by lambda emission is AT naught by ATE. Is it clear? Yes or no? Or shall I say it again? How many of you? This is very important concept of cosmology. Is it clear? Jahan, clear? Go.
Yes,
I'm just once you do that homework, I'm just multiplying both sides by c. and getting that peak between two emissions, that is the wavelength. So now you tell me, which one will be higher, observed or emission, by looking at this relation?
Observed will be higher.
Observed will be
Greater.
why? Because
Because 80 naught is greater
A
than.
naught is the expansion factor at later time, is greater than the expansion of the universe at earlier time. As we know that scale factor is increasing. Is it clear for everybody? Yes? So earlier they have emitted, the higher will be redshift. Clear? Yes or no? Yes, yes, say it. Yes? Earlier.
Yes.
So now
Yes.
we'll define a quantity with this A T naught by A T E. Now I'll go back to the, it's a pure definition. Just a definition, A T naught is 1 plus Z, and Z is called redshift. Till now it's a mathematical definition. I'm just redefining this ratio. Now, A T naught is 1, I have already told you today. And then if A T naught is 1, then I will not use ATE now onwards, I'll just use AT and not TE, because I'm just giving this. So let us go back again to my note. So AT naught divided by ATE is, this is the definition, no? Oh no, is the definition or the other way around? It is 1 plus Z, no? Not 1 by 1 plus Z, no?
Yeah, 1 plus Z.
1 plus Z. Sorry. So now AT naught is 1. So 1 by AT. So now onwards I will not give any E emission, because I am just removing the suppose at a time T, some star emitted light and we are receiving it at today, and today AT naught is 1. So we get this formula 1 by AT equals to 1 plus Z. So now, if AT is small, that means it has been emitted earlier. Suppose 10 to the power minus 3 at the time of CMB, some light is coming. So 10 to the power minus 3, it will go to the denominator, then 10 to the power 3. So Z will be how much? So this gives you a mapping between scale factor and the redshift Z. So can you tell me what is the redshift when CMB was emitted? What was the scale factor at CMB? I told you today, 10 to the power minus 3. So how much is the Z?
999.
Exactly. So almost 1000. Yes? What is the redshift of today? Today, so now if some light is emitted from today only, say just from sun or nearby, then AT you can take almost like 0, isn't it? Sorry, 1. Because it is very close by emission. So that means it is not far in the past. So universe does not change its redshift so early. So AT is 1. So for a given time, if AT is 1, then redshift Z is equal to how much?
0.
0.
So if at present time redshift is 0, so you can see now that Z becomes higher at earlier times. So when universe was 1/10 of the present time, the length, then redshift was how much? 10 minus 1, so 9. Clear? Because it is 10 to the power minus 1, 1/10 of the present time, universe was smaller. Then redshift was how much? This will become 10 is equal to 1 plus Z. So Z is equal to 10 minus 1 is 9. Is it clear now?
Yes, sir.
So now I'll tell you the star actually started forming at a redshift around 10 or 20. So universe was just 1/10 of the present time. Okay, that means the that is like 5-7 billion years back. So that means universe expansion is not very high. It has been expanding, it is stretching the wavelength, but not that much. But still it is a pretty big expansion because 10 times stretching of a wavelength is pretty high. Okay, when the stars form. So when the first star formed, that light, if it comes to Earth, it will be 10 times more than the wavelength. Okay. So today we have defined the concept of redshift from here today. Very important concept, redshift. So now I will not tell you the details. This note I will send you. You have to find out from redshift what is called luminosity distance.
Yeah, I've been using that thing.
Hello?
Sorry, sir. Sorry. Mic was unmuted.
Okay. So luminosity distance is nothing but that you will read from this note. It will be self-explanatory. Suppose at a distance R1, one star is emitting light. How much flux you will be receiving at the observer? It will be the P. P is the amount of energy emitted by the A. A is the surface area. So from there, you define luminosity distance. You read it. If you cannot understand, next class, I'll explain. Because this luminosity distance DL kind of tells you that how much the flux will be. You see, if from another stars the flux is coming, the more further you are, the flux will be dimmer because light will be 1 by r square, no? Like a torch light. It goes in every direction 1 by r square, the total surface area. So if you are away from a star, then you have to find out 4 pi r square distance from that star, and light intensity flux will be divided in every unit area. But on top of that, there will be an expansion of the universe that will also reduce the flux because the length scale is expanding. Is it clear? Yes? Is it clear? Yes. So normal torchlight flux gets reduced because of the area 1 by r square. But here you will get another factor a square because the distance is also stretching. So that's why if you go, this is your homework to study this part. You will see that it goes as another a square, 1 plus z square. This 1 plus z is a. And along with r1 square, you get 1 plus z square. So this luminosity distance dl square is actually the distance times 1 plus z. That means that is the stretching, this luminosity distance. So in cosmology, people don't talk about the actual distance. We talk about the luminosity distance because that is what matters for telescope to measure the flux of light. That how much was the actual distance times how much was the redshift. Means how far are they and how long the light is traveling, and that will become this. So this much for today. This part you don't need to understand now, the arc sine part. Next day onwards, we'll start the GR, okay? And find out a solution for scale factor of the universe A, and that is very interesting, okay? So this will be next class. So is it clear today that a lot of things we did? Now I have spoken a lot. Now you speak what are the things we have done today. Recap. Speak it. Till now you remember. Okay. What are the things without looking your notebook? Okay. We started from where? Who will speak or you can write it down. What are the things? You write it down, we done today. Or you can speak. Jahan, you are speaking? No. Shruti, so what are the things we have done? Okay, you are writing? No, nobody is writing. Recap time, last 5 minutes.
Sir, the metric and the curvature of space-time.
Metric and curvature of space-time. What else? Other people can write down. Yeah.
Redshift.
Redshift. How to derive redshift from the FRW metric? Yes. Did you know that before? How many of you did not know it? Know it before or no? Did not know it, no? No. You can say no. No, sir. Very nice. This is a very important thing. So see, we have not used anything. We have just used the FRW metric, universe homogeneous and isotropic. And from there, a trajectory of light ray d square equals to 0. You find out the idea that redshift can be defined as a stretching of wavelength. But that homework you have to do. Okay, Ravi, you will also do the homework. Okay, yes, okay, very nice. What else we did? We recap about different. Your homework is another homework is that 4 points of the universe. Ravi, can you write down to them in the to me? You write down later. I'll send them by email. You have to make a table of scale factor and time of different epoch. Big Bang nucleosynthesis, quark formation, CMB, and Higgs phase transition. Is it clear? Yes. What was the A at that time? Very nice. What else we did today? We did something called in the beginning that homogeneity and isotropy. We explained it in detail in cosmology, different length scale. You remember? So what is the length scale where cosmology works? Can you write it down? We discussed today.
Megaparsec, 10,000 megaparsec.
Maybe megaparsec. What is intergalactic distance? Average between two galaxies.
Few hundreds of megaparsec.
No. Intergalactic distance is kiloparsec. Galaxy is kiloparsec, so 100 kiloparsec or 50 kiloparsec. Megaparsec is cluster.
Yes, sir.
Yeah. Okay, done. What else we did today? Spatial curvature. K equals to 0, 1, and -1. Yes? Yes, that is also your homework. Universe as a whole, K equals to how much? 0. 0. But it is not the case near black hole or any case. But for the cosmology, we'll take it as 0. Clear? So is it clear now? You are getting that what is astrophysics and what is cosmology, what is redshift, how scale factor and redshift are synonymous. Okay, you can either use scale factor or use redshift, and how the wavelength gets stretched. And that's why if you measure the lambda observed and the lambda emitted, you can find that is called the spectroscopy of the stars. By looking at it, you can say, oh, that means this wavelength has been this much bigger. That means the star is this far away. Okay. But for that, you need to know the physics of the emission of the wavelength. Okay? Because one thing you have to pin down. If you don't know what will be the wavelength in the beginning, then you cannot say that how much. That's where the physics comes in. Suppose a Lyman alpha emission, you have heard about it, Lyman alpha emission? Yes, from hydrogen atom. So you know that from a hydrogen cloud, from intergalactic space, a Lyman alpha emission is coming. So you know that what is the wavelength of Lyman alpha. That is determined by the physics of the space between two atomic lines. Yeah. And now if you know how much there has been stretched, you can tell that means the cloud is at this redshift. Is it clear? Is it clear? Yes. Yes, because you know physics of the emission, that how much is the length scale, lambda. That's how the astrophysics works. So if you both are unknown, I'm telling you again and again, you only know the ratio from scale factor. Okay. So you need to know one point to find out the other one. Clear? Yes? Yes. Very nice. Okay. This much is done for today. Next class we'll do a little bit of GR idea, and we'll do Friedman equation of cosmology. Starting, it is derived from GR, and then we'll solve the AT, and we'll solve many more things. Okay, clear? But you have to do this homework I have given. Okay. Yes. Next class. Yes.
So near massive objects, the k value will be greater than 0, right?
K value
Is greater than 0. Is equal
Yes.
to 1.
Yes.
So is there any place where like k is less than 0?
It can be, depending on the open curvature. That we'll talk later. That's where the black hole physics come. But you will see that for all Schwarzschild black hole, what we know, its k is positive. Okay? But in some cases, k can be negative. That appears in string theory. Okay, some space become openly curved. Okay, we'll talk about it if we get time. Okay. But generally, for our Schwarzschild black hole or Kerr black hole, different kind of black holes are there. We'll talk about it. Near that, the curvature is positive. Positive means place is curved, space is curved, closed. Yeah.
So it is related to attractive gravity, attractive force, repulsive force.
Anti-gravity can make it. So wormhole area, you can get some negative curvature and all this thing, but that does not exist. So we don't know whether it exists or not. But anti-gravity can make it negative. But we don't know what makes anti-gravity. Okay. Yeah.
Okay, sir. Thank you, sir.
Okay, great. So I'll talk with you guys in email. Let's make an email group or a WhatsApp group, whatever it is. And yeah, Shruti can make the WhatsApp group or email group. And then you can, email group is also fine. There we'll email when is the next class. Okay? Okay. Next week again, maybe Tuesday or sorry, Wednesday afternoon we'll do next class. Yeah, okay, good. Okay. And the books, Physical Cosmology, Dodelson, Ravi, you can send an email in the group. I'll add Ravi's email ID in that group. Okay?
Yes, sir.